Hello, this is Virginia, and I'm here to show you how to do another test in SPSS 31. So in this data set, we have 38 participants, as you can see by the 38 rows, and we have average reaction times. This is the time it took them to type three different types of five-letter clusters. So normal means that the five letters made a normal word in English. Bigrams mean it was not a word, but it was something pronounceable like warp. And random means it was five letters that you could not sound out or using the rules of English, make a sound out of them. So we have no categorical variables here. We just have these three ratio variables, and we're going to compare them using repeated measures. Because we have three variables, we can't do paired samples because paired samples maxes out at 2. So go to Analyze, General Linear Model, Repeated Measures, and then you're going to name your factor. Now, factor can be a little confusing here because normally when we talk about factors, we're talking about different groups. We're talking about different conditions for between subjects. But this is basically how would you group these variables? What would you call what they have in common in order to compare them? And we're just going to use 5 letters as a factor. You could also use stimuli, you could use letter groups, whatever. Number of levels. So the levels are 1, 2, 3. That means 3 different variables. Click Add, click Define. And we only have 3 variables, so we're just going to highlight them all and put them here. We're going to click OK, and then I'm going to show you what you need to click on in order to get more information. Click OK, and the first thing you may notice is that there are a lot more numbers and a lot more output here than with one-way ANOVA. And the assumptions are looked at differently as well. So the first thing I want you to pay attention to is that each of these dependent variables, we have 3 dependent variables here. Our independent variable is letter group or 5 letters. They're numbered. This will be important when you're doing comparisons at the means level. This multivariate test section, you can just ignore that. That is looking at the intercept, which is really not something you need to report or worry about. Test of sphericity. This is similar to a test of homogeneity of variance or homoscedasticity in a one-way ANOVA or an independent samples t-test. This is seeing if the variance is similar enough in order to assume normality. Now, what you can see here is this is highly significant, meaning the variances are very different between or among variables. This is not shocking because reaction times tend to be fairly skewed. So I would imagine too that if you have some huge differences in behavior, you're going to have some big differences in variance. So we can't use this row here that says sphericity assumed. We go to the within subjects effects in order to find the f-test we're going to be reporting. And you might say, why does it even matter? Because the f-tests are all the same and the significance are all the same. Well, here the significance looks the same because the p-value is so very small that they all can be represented the same way. However, the p-value actually is adjusted, so you'll see that these bottom 3 rows are going to be small, or they're going to have larger p-values, so they are less significant. However, the f-test itself is not affected. Now, what you actually will need to know for the test of sphericity is that it will tell you which degrees of freedom to use. So for the most part, statisticians recommend using greenhouse gazer. There's some situations where Hunfeld can be used, but they're pretty uncommon. And generally speaking, lower bound is considered too conservative and too prone to type 2 errors. That is, that you're not going to be able to find an effect even when there is indeed an effect. So you would report this degrees of freedom, 1.17. And this degrees of freedom for your participants, 43.56. Now you can see there's a big difference there because SPSS in these calculations is using more degrees of freedom in order to get significance. We don't need to worry about within subjects contrast. That is one way in which you can compare which variable is different from the other. This is an omnibus test. It does not tell us where the difference is or the direction of it. It just tells us there is a difference somewhere in there. This can be used to interpret where the difference is, but I'm going to show you a much more straightforward way to go about that. Here are between subjects effect. We don't have anything here because we're not comparing any between subjects effects. That is for a mixed ANOVA. So now let's redo this so we can actually see where the difference is coming from. So we go to General Linear Model, Repeated Measures. We can just go ahead and click Define. Got everything where it's supposed to be. Post hoc is for between subjects. So we do not use post hoc unless we're making between subjects comparisons as well. We click on EM means. That means estimated marginal means. And this will compare the means pairwise for the three variables. Now we want to click compare main effects because we want to compare the simple main effects of each of these means. And we need to adjust the confidence interval. This is similar to how we adjust for multiple comparisons when we're doing a between subjects analysis using ANOVA. Just like with one-way ANOVA, LSD is too liberal, too prone to type 1 errors. Bonferroni is too conservative, too prone to type 2 errors. SIDEC is the just right, medium level, middle of the road, moderate approach. So SIDEC is what I would recommend. Click continue, click OK. Now up here where the dependent variables are numbers, this will be important because as we scroll down here to our pairwise comparisons, you'll see that unlike with one-way ANOVA, where the conditions are labeled by their name in the pairwise comparisons, in repeated measures, they are just given the number. And what you can see here is this is variable 1 compared to variable 2, variable 1 compared to variable 3. They're all highly significant, and it's not surprising when you look at how much bigger the mean differences are than the standard error. So oftentimes I will just write down what my variable numbers are because scrolling back and forth can make it easy to lose track of what I'm trying to analyze. Now here are the means of each of the variables. So we can see right there that number 3 is the slowest. That's the one where it's random letters. And number 2 is the fastest. And that's where it's actual words. Let's graph those. Let's go to graph. We want bar graph. And we want a simple graph because we're not looking at any clustering together. Now, we're not looking at groups of participants, we're looking at separate variables. These are 3 different variables. All the participants experienced each of them and reported each of them. We'll click define. We only have 3 variables, so they're easy to find, and click over, and we have our means. Now, I'm always a fan of reporting your error bars so you can better visualize the effect because a mean difference is only as meaningful as the number of standard errors or standard deviations that are represented by it. Click continue, click OK, and we can see here that random is the slowest, normal is the fastest, bigrams, where there are 5 letters that can make a sound or pronounced in English but aren't actually English words, was in the middle. You can also see with the error bars that it's not surprising that all of these pairwise comparisons were indeed significant.